Hello everyone and welcome to Control Engineering Tutorials. In this tutorial we will provide correct and intuitive explanation of observability of linear dynamical systems. In particular, we will answer the following questions. Question number 1. What is observability of linear dynamical systems? Question number 2. How to properly and intuitively understand the concept of observability of dynamical systems. Question number 3. How to test the observability of dynamical systems numerically. Question number 4. What is the connection between observability and conditions for the unique solution of systems of linear equations? Due to the complexity of observability, I will split this tutorial into two parts. In the first part that you're currently watching, I will introduce the concept of observability. And in the second part, I will explain how to test observability of a system in Python. Links to both parts will be provided in the description below this video tutorial. However, before I start with explanations, I would like to mention the following. It took me a significant amount of time, energy, and planning to create this completely free video tutorial, as well as almost 400 free video tutorials that you can find on my YouTube channel. And consequently, I kindly ask you to press the like and subscribe buttons. Thanks a lot! Let us first motivate the observability problem by considering this example. Over here, you can see two masses, M1 and M2, that are connected by springs and dampers. S1 is the position of the mass M1 with respect to its equilibrium position. S2 is the position of the second mass with respect to its equilibrium position. First, we will clarify what are the states of this system. The states are x1, the position of the first mass, x2, the velocity of the first mass, x3, position of the second mass, and x4, the velocity of the second mass. The state vector then looks like this: x1, x2, x3, and x4. Let us assume that we want to design a state feedback controller that will take the state information of this system, that is, it will use the complete state information to stabilize the system or to achieve the desired tracking performance. To develop such a controller, we need to provide information about the state. This means that we either need to directly measure all the state variables x1, x2, x3, and x4, or we need to reconstruct them from available measurements. The easiest solution to this problem would be to place 4 sensors over here, and every sensor should measure the corresponding state variable. For example, the distance sensor should measure S1, then another distance sensor should measure S2, then the velocity sensor should measure S1 dot, and another velocity sensor should measure S2 dot. That is 4 sensors for 4 state variables. Is this possible in practice? Well, it is. It is if you have $1 million and if you can spend that money to develop such a complex sensing system. However, most likely in practice we will work with a limited budget. And we will have enough funds only to purchase a single sensor. Let's say that we purchased a distance sensor. And let's say that we placed this distance sensor over here. And this distance sensor provides us information about S1. Now we ask the following questions. Can we reconstruct the complete state vector by only observing the position state variable x1 or s1? That is, can we compute the velocity of the first mass as well as the position and velocity of the second mass by only observing the position of the first mass? If not, then in addition to the state variable x1, we need to observe another state variable. That is, we need to purchase another sensor. For example, let us assume that we purchased another distance sensor and that we use that distance sensor to observe S2. Now we pose the following question. Can we observe, that is, can we reconstruct the complete state vector by directly observing x1 and x2? If yes, how many data samples of the observed state variables we need to have to completely reconstruct the state vector? If we have the proper understanding of observability concept and if we know how to use the observability analysis, we would be able to answer these and similar important questions. That is, we would be able to design a complete state feedback controller. Okay, in the sequel we present the theoretical explanation of observability. The easiest approach for understanding observability is to start from a discrete time state space model given by this equation. Over here, xk is the state vector at the discrete time instant k. A and C are the system matrices, and yk is the output, and k is a discrete time instant. The elements of the output vector are actually observed state variables. For example, in the case of the mass spring damper system that's shown previously, if we measure only x1, then yk will be equal to x1. And in that case, the C matrix will look like this. 1, 0, 0, 0, multiplying x1, x2, x3, and x4. And this gives x1. To summarize, in a practical scenario, the vector yk is a vector of quantities that are observed by sensors, and the state is either a physical state, for example, involving mechanical quantities, or the state is linearly related to the physical state through some matrix, which is usually known as a similarity transformation. Here's the first question that we need to clarify. Why is it easier to understand the observability concept by considering discrete time systems? This is because it's easier to propagate the dynamics and equations of discrete time systems over time. Namely, we can establish recursive relationships connecting different quantities at different time steps. We just perform back substitution to relate quantities at different time intervals. This will become completely clear by the end of this tutorial. Here, I will briefly illustrate this. For example, let us start from this state space model. And let's propagate the state equation. As the result, we obtain this chain of equations. What's happening over here? Let's see. The state equation has this form. And if I start from the time step k is equal to 0, I will have x1 is a x0. Then I will have that x2 is a x1. And this is nothing less than this part over here, right? So I have a times a x0, and that's precisely a squared x0. And by continuing this process, I will obtain that xl, where L is some discrete time instant in the future, is a to the power L times x0. On the other hand, for linear continuous time systems, it's more challenging to establish such relationships since we need to use integrals and differential calculus. For example, a continuous time equivalent of this equation is this equation. The state at continuous time instant t is e to the power ac times t multiplying x of 0, where x of 0 is the initial state. Over here, AC is a continuous time system matrix of the classical linear system, and you can see this equation. This equation involves an exponential of a matrix, and it's way more complex. Consequently, the observability derivation is also a little bit more complex. The results at the end will be the same. That is, you will see that the structure of matrices for testing observability are the same in the case of discrete time and continuous time systems. However, the derivation of observability conditions for continuous time systems is a little bit more complex, and it's not for complete beginners. Consequently, if you're a complete beginner, start with observability analysis for discrete time system, and you will obtain a very intuitive understanding of observability. Here's the second question that we need to address. Is there a reason why we are not taking into account inputs when analyzing observability? Let's go back to our state space model. Here it is. Often in literature, you will see this term over here, plus B times UK, where B is the control input system matrix and UK is the control input vector. So why I'm not including this term in the observability analysis? The answer is that known control inputs can easily be included as known quantities when analyzing observability, and we can subtract their effect from the observed outputs, and the resulting quantity can be used to derive the observability condition, which is practically independent of the control inputs. That is, the inputs do not affect the observability rank test, and when analyzing the system observability, we can safely neglect inputs. Now we are ready to formally define observability. The state space model, given by this equation, is observable if any initial state of the system, denoted by x0, can be uniquely determined from the set of output observations y0, y1 until ys, where s is a positive integer. Here is a graphical explanation of this important definition. By using sensors, we collected a time sequence of observed outputs. That is, we collected y0, that is the output at the time instant 0, y1, that is the output at the time instant 1, y2, that is the output at the time instant 2, until ys, that is the output at the time instant s. And knowing this sequence of observed vectors, we want to uniquely reconstruct the initial state of the system. That is, the system is observable if the initial state of the system can be uniquely determined, estimated, or reconstructed from this sequence of observed outputs. To summarize, from this definition, we can conclude that the observability problem is closely related to the problem of estimating the state of the system from a sequence of output measurements. Secondly, we can observe that in the definition of observability, there is a parameter S. This parameter is the length of the observation horizon. Its length generally depends on the number of observed outputs of the system, the structure of the system matrices A and C, and on the state dimension. There is a common misconception among control engineers that S needs to be at least equal to n-1, where n is the state dimension of the system, to make the system observable. Keep in mind this. A lot of people think that in the general case, the length of the observation horizon S needs to be equal to at least n-1. However, this is a misconception. To show this, let us consider this system. Over here, I have a second order system with an arbitrary A matrix. And let us assume that C matrix looks like this. It's a diagonal matrix where Kn1 and K2 are non-zero constants. The meaning of this equation is, we directly observe scaled states variables since the matrix C is a square 2 by 2 matrix. In addition, due to the fact that the constants k1 and k2 are non-zero, the matrix C is invertible. And consequently, from the equation 6, we can write this equation. By just substituting y0 here, we obtain this equation. And x0, of course. This is a system of two equations with two unknowns. The unknowns are the entries of x0. Since the matrix C is invertible, there is a unique solution of this system, and it's given by this equation. And consequently, we observe the following. We can observe the initial state by taking only a single sample, y0, of the observed outputs. Okay, let us now derive a general condition for testing observability. We will derive the so-called lifted state space description. The description is called lifted since we lift the state space model over time to obtain a batch vector consisting of output samples. From our state equation, we obtain this sequence or this chain of equations. y0 is cx0. y1 is cx1, and that's equal to cax0. To clarify this, let us write our state space model once again. I have xk plus 1 is equal to axk, and I have yk is equal to cxk. From this equation, I can just substitute 0 over here to obtain this equation. How about this equation? What happened over here? Well, first step, y1 is equal to cx1. However, then we know that x1 is actually ax0, and we substitute this equation over here to obtain this equation. How about y2 is equal to cx2? Well, y2 is equal to cx2 by using this equation, and again, we backpropagate. We know that x2 is ax1, and by using this equation and the output equation, we actually obtain this equation, and then we simply can substitute this equation over here to obtain this part. And by using this recursive back substitution, we will obtain this final equation. ys minus 1 is ca to the power s minus 1 x0. This chain of equations can be compactly written like this. I'm just writing the chain equations in the vector form. I take y0, y1, y2 until ys minus 1, and I group these quantities in a vector. And on the right hand side, I have this matrix multiplying a vector. More compactly, this equation can be written like this. And let's explain this notation. In control theory, when you see something like this is usually a lifted vector. This means that this vector consists of other vectors that are stacked on top of each other, starting from the time index 0 until the time index s minus 1. And then you have this matrix multiplying x0. This matrix is actually called s minus 1 step observability matrix. It has this structure, and this vector is s minus 1 step lifted output vector. This equation represents a system of equations with unknowns that are the entries of the vector x0. That is, in practice, this part is known. Since we can observe the outputs over time, we know the model of the system. Consequently, we can construct this matrix, and we want to determine x0. From everything stated up to now, we can conclude the following. We can conclude that the observability problem is equivalent to the problem of the existence and uniqueness of the system of equations 11, or in the compact form 12. We need to determine the conditions that will guarantee that this system of equations will have a unique solution. In order to find the correct value for S, let us analyze the dimensions of the system given over here. this system has to have at least as many equations as the number of unknowns. We have in total s times r equations and we have n unknowns. Why s times r? Okay, the dimension of every y is actually r, and we have s entries over here. Consequently, we have s times r equations. How about unknowns? Well, the unknowns are the entries of the vector x0, and consequently, we have n unknowns. We can also allow for more equations than unknowns. This means that the necessary condition is that s times r should be greater than or equal to n. In the case of single input, single output systems that are often abbreviated as SISO, we have that r is equal to 1, and consequently we have to have at least s greater than or equal to n. In the case of multiple input, multiple output systems, depending on r, we can also allow for s smaller than n, as long as the underlying linear system of equations has at least the number of equations equal to the number of unknowns. And this is the example that we considered previously. However, since we want to derive the general condition that will be applicable to both single input, single output and multiple input, multiple output systems, we have to take s greater than or equal to n. But do we really need to select s such that s is larger than n? The answer is no. There is a theorem called Cayley-Hamilton theorem telling us that every matrix satisfies its characteristic polynomial. This means that we can express the powers of ai, where I is greater than or equal to n, as linear combinations of powers of a smaller than n. This implies that any block row of the observability matrix after this block can be expressed as a linear combination of previous rows. Taking this analysis into account, we can safely select s is equal to n. Then our system has this form, where this vector is defined over here and the matrix is defined over here. Now we have to address the following question. What is the condition that the matrix On minus 1 needs to satisfy such that this system has a unique solution? This theorem answers our question. This is the observability condition theorem, and this is a classical result in control theory. It goes like this. The system of equations 14, that is, this system of equations with the vector y defined like this and the matrix On minus 1 defined like this, has a unique solution if and only if the rank of the n minus 1 step observability matrix is equal to the state order, that is, it's equal to n. That is, the system is observable if and only if this rank condition is satisfied. In other words, if the matrix On minus 1 is a full column rank matrix, then the system is observable. And the other way around, if the system is observable, then the matrix On minus 1 is a full column rank matrix. Over here, I will only prove that the rank condition, that is, this condition, will guarantee the observability of the system. Let us assume that the condition 16 is satisfied. Then, let us multiply the equation 14, that is this equation, by On minus 1 transpose. And as the result, we obtain this equation. Since the rank condition is satisfied, the matrix On minus 1 transpose times On minus 1 is invertible. And consequently, the system of equations 17, where the unknown is x0, has a unique solution, and this solution is determined by this equation. And that's it. We have shown that if this condition is satisfied, there is a unique solution, and this unique solution is given by this equation. Okay, that would be all for today. I hope that you like this video. If you like the videos I'm creating, please press the like and subscribe buttons. Thanks a lot and have a nice day.